This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to cover Newton's second and third laws. So make sure that you've watched my video on Newton's first law before you watch this one. So, what was Newton trying to figure out? Newton was trying to figure out what causes acceleration. And so we want to just remember what we mean by something accelerating. If an object is accelerating, it's either speeding up or slowing down. So remember that in physics, whether we have a positive or negative acceleration, we just call it an acceleration. So if the velocity is changing, the object is accelerating. So what will cause an object to accelerate? The answer that Newton found is that if there's a net force acting on the object, then the object will accelerate. So the acceleration somehow depends on the net force. And remember from our previous video, net force just means the vector sum of the forces acting. And we'll look at some examples of that. So, the next question, does the same force have the same effect on different objects? Well, I think you probably already have a pretty good sense that it doesn't. In other words, imagine two scenarios. Here you are, and you're asked to exert a force on a baseball. So you've got a ball, and you exert a force on it. It's very easy to accelerate that ball. In other words, to get that ball moving, to change its velocity. But what if instead you exerted the same force on a car? Well, even if the car was in neutral and the brake isn't on, if you exert the same force on that car, you're certainly not going to get that car moving as fast as you can get the baseball moving. And so what we're going to find is that the effect that the net force has is going to depend on the mass of the object. So it makes sense that if the mass is smaller, it's easier to get it to move. Remember, that's that concept of inertia, the tendency of an object to want to stay either at rest or stay moving if it's already moving, that we talked about previously. So let's look at Newton's second law. Newton's second law says the acceleration is equal to the net force. Again, that's the sum of all the forces acting. And because forces are vectors, we have to pay attention to the direction. So the net force divided by the mass of the object that we're exerting the force on. So in the case of trying to push the car, the mass is the mass of the car. You'll also notice that from a units perspective, we know that acceleration is measured in meters per second squared. Remember, we always can think back to that really means meters per second per second. In other words, how much the velocity is changing per second. We know that force is measured in newtons, and mass is measured in kilograms. Okay? So remember, in the SI system of units, the basic unit of mass is not the gram, it's the kilogram. So newtons divided by kilograms are equal to meters per second squared. Now, when you look at Newton's second law, that an acceleration is caused by a net force, one of the things to think back about to our previous video is Newton's first law. And you'll notice that Newton's first law is actually just a special case of Newton's second law. We can see that because remember that Newton's first law says an object will stay at rest or stay in motion with constant velocity unless acted on by a net force. So notice in Newton's second law, if we set the net force equal to 0, then the acceleration has to be 0, right? If F net is 0, then A is definitely 0. Well, if the acceleration is 0, that means the velocity can't be changing. So the velocity has to be constant. And of course, a special case of the velocity being constant is that there's simply no velocity at all. And so we can see that an object will remain at rest or remain moving with constant velocity if there's no net force. And again, that's really just follows directly from Newton's second law. Let's try out a problem. A toy car with a mass of 2 kilograms is pushed from rest with a force of 6 newtons. What is the acceleration of the car? So we'll write down Newton's second law that the acceleration is equal to the net force divided by the mass. And in this case, we've been given the net force. The only force acting on the car is that force of 6 newtons. And the mass of that toy car is 2 kilograms. And so again, when we take newtons and divide by kilograms, that gives us meters per second squared. Now, once we have that, you'll notice that we can answer questions with kinematics as soon as we know the acceleration. So for example, here it says, if the car starts from rest, how fast will the car be moving after 5 seconds? Well, one of the formulas that we learned when we learned one-dimensional kinematics is that the final velocity is equal to the initial velocity plus the acceleration times the time of the motion. And so in this case, notice that it starts from rest, so v naught is equal to 0. And so we get v is equal to 0 plus our acceleration, which is 3 meters per second squared, times that time of 5 seconds. And that would give us a final velocity, v, of 15 meters per second. Okay. Let's look at another problem. This one is just a little bit more complicated because we've got two forces acting. It says a toy car with a mass of 2 kilograms is pushed from rest with a force of 6 newtons. The force of friction on the car is 2 newtons. What is the net force? So one thing to always remember about friction. Friction always acts in the opposite direction of the motion of the object. Okay. So whenever we have a friction problem, we always know that friction is going to be in the opposite direction that we're trying to make the object move in. So here's our car, and we can picture that we're exerting a force of 6 newtons to make that car go to the right, but there's a force of friction which would be in the opposite direction of 2 newtons. And so to figure out the acceleration, again, we're going to use Newton's second law, that the net force over the mass is equal to the acceleration. But now the first thing we have to do is figure out what is the net force. Well, we got a force of 6 newtons to the right. We're going to subtract that force of 2 newtons because it's in the opposite direction. And then we're still going to just divide by 2 kilograms. And so what we end up with is 6 minus 2 is 4. 4 divided by 2 is 2. So we get 2 meters per second squared. And again, we could now figure out how fast the object is going to be going after a certain number of seconds if we were asked to do that by using our kinematic equations. Let's talk about Newton's third law. One of the things that Newton realized when he was thinking about forces is that forces always occur in pairs. And so I give you some examples here. I push on the wall pushes back on me. In other words, if you picture yourself kind of leaning against the wall, you're definitely pushing on the wall, and you're pushing in this direction. But you would fall down unless the wall, or you would fall down if the wall weren't pushing back on you. So whenever you exert a force on something, it exerts a force back on you in the opposite direction. Imagine you're now pulling on something. It's pulling back on you. So here's some other examples. When hitting a baseball, the bat pushes the ball pushes back on the bat. You can actually see that the ball exerts a force on the bat, if you examine a wooden bat that's been used for a while, you'll see it's got a lot of dents on it. So the ball exerts a force on the bat, but the bat also exerts a force on the ball. Just think of yourself sitting in a chair right now. Your weight is pushing down on the chair, but the chair is also pushing up on you. Or if we picture somebody standing, your weight is pushing down on the floor, but the floor is pushing up on you. So forces always come in pairs. So what Newton's third law says is not only do forces always come in pairs, but the forces are always equal in magnitude and opposite in direction. So back to me pushing on the wall. If I'm pushing on the wall with a certain force, let's say I'm pushing on the wall with a force of 5 newtons, the wall is pushing back on me with a force of 5 newtons. So not only are they in opposite directions, but they're equal in magnitude. The way Newton actually said this was he said, to every action there's an equal and opposite reaction. And in fact, that expression got into kind of everyday speech, so you may have heard that before. But what Newton meant by action and reaction, that was just his word for force. So for every force, there's an equal and opposite force. But again, think of it this way. If I exert a force on the wall exerts a force back on me. If I push down on the ground pushes up on me. Those are action-reaction forces. So let's look at an example that illustrates Newton's third law, and one of the things that is confusing about it. So here's the question. When a mosquito smashes on your windshield, which experiences more force, the windshield or the mosquito? Now, if you ask a friend who hasn't had a physics course before, they would probably naively say the mosquito experiences a greater force. Because after all, that little mosquito flying along gets smushed on your windshield, and your car doesn't really even notice that anything happened. However, Newton's third law tells us that the force that the car exerts on the mosquito and the force the mosquito exerts on the car have to be the same. So what's different for the car and the mosquito? And the answer is the accelerations are going to be different. So in other words, let's look at the mosquito. If we write down Newton's second law for the mosquito, we've got the force that the car exerts on it. So that's car on mosquito. But then we divide by the mass of the mosquito. Well, the mass of the mosquito is little, right? I'll draw it by a little m. So when we have a bigger number divided by a little number, remember that gives us something big. The acceleration of the mosquito is going to be big. However, let's look at the car. If we look at the acceleration of the car, we've got that force. That's the mosquito on the car. But that's, it's not a very big force relative to the car. The mass of the car is huge. I'll write it with a really big M. And so we've now got a smaller number over a bigger number. We have something that's very small. And so if you think about it, you're driving your car and you hit a mosquito. Your car doesn't slow down. Now, if you hit something like a deer, you would notice and your car would slow down. On the other hand, the little mosquito, think about him. He was flying along towards the car, and now, boom, he gets stuck to the car and is going the other direction. He had a big change in velocity, a big acceleration, and that ultimately is what kind of obliterates the poor mosquito. Let's look at another example. A rifle fires a bullet. What are the action and reaction forces? So the first force that we'll talk about is the force that the rifle exerts on the bullet. So obviously, the gunpowder goes off, the rifle is exerting a force to the right on that bullet and making it go to the right. But the bullet exerts a force on the rifle. And Newton's third law tells us that those forces are equal and opposite. So again, those forces are equal and opposite, but the results for the two objects are very different. Again, think about the bullet. The bullet is going to have a really big acceleration because the force that the rifle exerts on it is going to be big compared to the mass of the bullet. The mass of the bullet is going to be small. So we get a big number. But for the rifle, the mass of the rifle is big. So the acceleration of the rifle, even though the force on it is the same, since the mass of the rifle is big, the acceleration is going to be small. Now, it's not zero. If you've ever fired a gun yourself, or you've seen somebody fire a gun, or you can picture watching a cannon fire a cannonball, you'll notice that the gun always gets pushed back. It recoils. Well, now you understand why, because there is a force back on the gun that is the same as the force on the bullet. It's just that the gun has so much more mass that acceleration is small. And you can probably figure out the answer to this last question. Would it be a good design if the rifle and the bullet have the same mass? And of course, the answer is no, because if they had the same mass, then they'd have the same acceleration. The bullet would go off and the rifle would go off at the same speeds, and that's not what we would want to happen. So let's try out a problem that ties together these concepts that we've been learning. An orderly pushes a stretcher. The stretcher has a mass of 25 kilograms, and the patient that's on board has a mass of 52 kilograms. And the orderly, she exerts a force of 100 newtons on the stretcher, and there's a force of friction on the stretcher of 15 newtons. So we've got a number of questions to answer. What's the net force acting on the stretcher? What's the total mass that the orderly is pushing? What's the acceleration of the stretcher and patient? And then what force does the stretcher exert on the orderly? So first, let's start with figuring out the net force on the stretcher. I'll just represent the stretcher here with a dot. And we can see the orderly is pushing that stretcher to the right with a force of 100 newtons. However, we've got friction. Friction always opposes the direction of motion. So we've got a force of friction of 15 newtons to the left. And so you'll notice that the net force is simply going to be 100 minus 15, or 85 newtons. So that's the answer to our first question. The next thing that we need to know is, what is the total mass that the orderly is pushing? And we need to know that total mass because ultimately we want to calculate the acceleration. So that total mass is just the mass of the stretcher itself, which is 25 kilograms, plus the mass of our patient, which is 52 kilograms. And so we get a total mass of 77 kilograms. Okay, so we've got the net force and we've got the mass. And so now we can go ahead and use Newton's second law to find the acceleration. So we know that acceleration is equal to the net force divided by the mass. And in this case, we know that the net force is 85 newtons, and the mass was 77 kilograms. And therefore, the acceleration, if you plug that into your calculator, you should get 1.1 meter per second squared. Okay, so that's that question. And then the last question was, what force does the stretcher exert on the orderly? Well, this is an example of Newton's third law. Again, the orderly is exerting a force of 100 newtons to the right. From Newton's third law, the stretcher has to be exerting an equal and opposite force of 100 newtons to the left. And so our answer for that last question would be 100 newtons to the left.